Welcome to today's tutorial. This week we're going through the fluid flow losses. So I hope you've all covered the lecture notes. We're going to go through the tutorial now. So we're going to start with example 2.5. What I'm going to do is just take a screenshot of it and bring it to the whiteboard, and then I can scribble all over it. It's pasted here somewhere. Bigger so I can read it. Alright. So this is the first one. This is what we have. So I have water at 25 degrees. It's pumped at a rate of 25 litres per second, going from the pond up to a tank. I've got the diameter of the pipe, the length of the pipe, the type of the pipe. So it is galvanised steel, so that's important. We've got some fittings in here. We've got 6 screwed sockets. We have a globe valve that's 3/4 open. And allowing for clogging, the K factor for the foot valve is to be increased by 1/3. Calculate the head loss. Alright. So what do we know? Well, I know Q is 20 litres per second. Alright, I have a diameter of my pipe. It's 100 millimeters. I have a length L is 60 meters. And everything else comes into account later. So let's start off and let's work out the velocity. So V is equal to Q on A. Hope you guys are familiar with this by now. 20 by 10 to the negative 3 to get to meters cubed per second, divided by pi d squared, 0.1 squared, all over 4. Punch this into your calculator and you should get 2.55 meters per second. That's our velocity. Now, what I need to work out is, what I'm trying to calculate is my Reynolds number, RE. Alright, so this here is the velocity by the diameter by rho all over the dynamic viscosity. So this formula here is in your notes. You should be familiar with it by now. I need to work out rho. Now, rho of water is typically 1,000, but my water is at 25 degrees. So I have to go find this. If I can find where the 25 degrees sits, I can find my rho, I can find my viscosity. So let's go find it. Now, it's in our first week notes in the appendix. Alright, we have the properties of water at various temperatures. So temperatures here, going for 25. So at 25 degrees, my density is 997 kilograms per meter cubed. So it's not quite 1,000, drops off a little bit. And my dynamic viscosity is 0.89 times 10 to the negative 3 pascals per second. So let's use them. And let's come back here. So I have V, 2.55 meters per second, by my diameter, it's 100 mil, by rho, which was 997, all divided by 0.89 by 10 to the negative 3 pascals. This comes in at, look at my calculator, 2.55, 0.1997 divided by 9, 10 to the negative 3. Where are we? We have 2.86 by 10 to the power of 1, 2, 3, 4, 5, 10 to the power of 5. Alright, so that's what we have. So I got my Reynolds number. Now, what I'm trying to work out here is trying to work out my loss. So I've got 2 types of losses, remember. I have my loss due to friction in the pipes and my loss due to all of my fittings. So to work out my friction loss, I need my Reynolds number, and I also need my relative roughness. So I need to work out my ER. Alright, which is the absolute roughness divided by the diameter. So the diameter is 100 millimeters. That's the pipe diameter. Now I've got to work out my ER. So going from the Moody diagram before, for galvanized steel, it is 0.15. Alright, this is why we highlight it's galvanized steel. This here equals 0.0015. So using the Reynolds number and the relative roughness, I can now go to the Moody diagram. So let's go find Moody. Where are we? Moody diagram. Here we are. So let me just rotate it so we can see what's going on. This is what we have. Alright, so my roughness E for galvanized iron, 0.15. This is where that value came from. I've worked out my Reynolds number, which was 2.86 by 10 to the 5. So 2.86 sits in here somewhere. Alright, so we draw a line the whole way up. And then my relative roughness sits about halfway here. So follow through. Alright, wherever they meet, come straight across. And you'll find they meet about here somewhere. Come straight across, and what we're going to get is 0.0. So friction from Moody is equal to 0.0225. And that's from Moody diagram. Alright, so that's my friction factor. Now, once we've calculated this, alright, what we can do is we can calculate our K value for our fittings, or we can calculate the loss, the head loss due to the pipes here now, if you want to, which is probably what I would do. So what I would do is my head loss due to friction is equal to F, the length divided by the diameter, V squared on 2G. Remember, what we're doing is we're converting our loss of energy into a meter equivalent so we can punch it back into Bernoulli. So what I have, 0.02225. The length, it's going to annoy me. The length, which was 60 meters, all over the diameter in meters, times by my velocity, 2.55 squared, all divided by 2 times 9.81, which equals, let's punch that into a calculator, 0.0225, 60 divided 0.1 times 2.55 squared divided by 1.81, and I have 4.474 meters. So that's my energy loss due to friction. Now what I need to do is I need to go worry about my fittings. So I have all these different fittings here. Alright, elbows, valves, gate valves, a strainer, a couple more elbows, another gate valve. So I have to take into account for these. Alright, so let's not forget this number here, 4.474. I'll just write that down as well. 4.474 meters. Alright, now let's go work out our fittings. So going by the question and what we are told. Alright, I have 6 screwed sockets. I have 1, 2, 3 elbows. Alright, so I can just count them because remember we're looking at the sum of K. Gate valve, a globe valve, a gate valve. So 2 gate valves, 1 globe valve, and a hinge foot valve. So what we do, and the way that I need you guys to set these up, so you know there's no confusion to it, I'll do it in green, I have my fitting. I have my K factor. I have my number or my quantity. And then I have my sum of K. So let's look at the first one. Let's start from the bottom of our network. So what I have is this hinged foot valve with strainer. So my hinged foot valve. With strainer. Now the K factor for that, where do I find it? Well, in our lovely notes that we have, in the appendix, we have factors here and factors here. For this example, these are the ones that we're going to be using. Alright, so what I have is my foot valve with strainer, hinged or swing disc, has a K factor of 3. So that's what I'll be using. But just be aware, for this case here, what we're told is to allow for clogging, the K factor of the foot valve strainer is to be increased by 1/3. Alright, so how do we increase it by 1/3? Well, the K factor is 3 times 4 and 3, increases it by 1/3, our K factor is 4. How many foot valves do we have? I've got 1, so my sum of K is 4. Let's keep going. I have gate valves, so gate valve. Alright, come here and find my gate valve. It's gate valve fully open, 0.2. How many do I have? I have 1 and I have 2. So I have 2 of them, so sum 0.4. Alright, I'll do one more and then I'll speed up, and I hope you guys are getting the pattern here. Alright, my next one, let's go with the 90-degree elbows. Degree elbow, we're not told it's a long radius, so we assume standard, worst case scenario. Standard is 0.6. How many do I have? 1 elbow, 2 elbows, 3 elbows. So 3 elbows, so my K is 1.8. Alright, and now I'll speed up. So I have my globe valve. I have some screwed sockets. And I have a sudden exit. Cool, so my globe valve is worth 8, I have 1 of them. Screwed sockets, alright, just reading these off the table, counting how many it's given in the question. Now, my sum of K down the bottom, so I add all of these up. So what I'm doing is adding all of these. That equals 15.38. Alright, so now what I have is my HL, so my losses due to my fittings. Hope you guys remember the formula for it. sum of k is relative to the velocity head, which equals 15.38, 2.55 squared all over. Alright, so 15.38 5.097 meters. Alright, so now my total loss, because that's what we're after here, calculate the head loss. So my head loss is equal to my head loss due to friction plus my head loss due to my fittings, which equals 4.474. .097 4.474 plus 5.097, what we get is 9.571 meters in total. Okay, so the other way that you could have done it, if you'd gone through, you can use the overall formula, which is, I'll put it here in blue, HL is equal to F L on D plus the sum of K, because they're both relational or proportional to the velocity head. So you could punch them straight into this formula and you should get the same answer. Either way you want to do it is fine. So that's how we solve this first question here. Okay, so let's go through and let's look at the next one. Let's just clear this. Tutorial. So next question here, determine the equivalent length of the fittings used in the system given. Determine the head loss using the equivalent length. Alright, so now I'm hoping I can undo that, which I don't know if I can. Oh, there you go, I can, beautiful. So what I need to do is I want to work out my equivalent length if my fittings, or the length of pipe, the loss due to friction equals the loss due to the fittings here. So how do I do that? Alright, in our notes, I think it's page 12, with this formula here. Alright, so an equivalent pipe length, this is the formula here that I'm going to use. My equivalent length is equal to sum of K times by the diameter divided by the friction. So let's do it. Okay, so this is for 2.6 example. So what I have, my equivalent length is equal to sum of K of the fittings times the diameter divided by my friction, 15.38 times 0.1 divided by my friction coefficient, which was 0.0225. Equals 68.36 meters. Alright, so how do I check that? Well, what I can do is now I can check my total head loss. Alright, just going by friction if I add this length back in to my original system. So F is L on D, this is our friction loss, V squared on 2G. The thing here that changes is my L. My L is now the equivalent here, so it's L plus LE. So it's my friction loss. What we've done is we've replaced the fittings, or the losses due to fittings, with an equivalent length of pipe times 60 plus 68.36. Alright, and God willing, what we should get is this here, the same number is what we're after. If it doesn't, we're in trouble. It should be very close. Alright, we should only have rounding error. 60 plus 68.36 divided by... Oh, Nathan obviously can't enter in on a calculator properly. 68.36 divided by 0.1 times 0.0225. 2.55 squared divided by 2.2 times 9.1. And what do you know? What do I get? 9.571 meters. Beautiful. So they're the same. Happy days. Back to the tutorial. Our next question. What we're going to tackle is, let's tackle 11.4. Alright, these here aren't overly difficult, so let's go through it. What I might do is clear this again, and I'll just copy paste it across. Control V. Alright, so I have a system for pumping water. I have 60 meters of 100 mil diameter galvanized steel pipe. I've got some fittings attached to it. Determine the head loss for the system. I've got a flow rate. Alright, one gate valve is open and the other half's closed. And I've been given the viscosity of water, which is nice. So let's go through. First thing I need to do, I'm given Q. Alright, that's Q. This here is the viscosity. Alright, that's written in there, which is nice. All of these here. K. This here, looking for friction loss. Alright, so V, my velocity is Q on A, which is 20 by 10 to the negative 3 divided by pi D, which is 100, D squared on 4, which gives me, how good is that? Same as the last one, meters per second. Now, what I need to do is I need to work out my viscosity again. Sorry, this is my viscosity, my dynamic viscosity. I need to work out my Reynolds number. Reynolds number and relative roughness. So let's go through. Let's calculate RE. Alright, rho, velocity, diameter by viscosity equals, alright, so what have we got? Water. Alright, if it's water, I'm not giving a temperature of it, it's safe to assume it's 1000. 2.55, 0.1, all divided by 0.9, 10 to the negative 3. Now remember, Reynolds number is dimensionless, so 2.83, 10 to the power of 5, my Reynolds number. Now what I need to do is I need to go through and I need to work out my relative roughness. Alright, I want to work out my ER. Galvanized pipe, my absolute roughness is 0.15. For the diameter. Alright, so now that I have my Reynolds number, I have my relative roughness. We go visit my ex-misses and we go to our Moody diagram, which is on, which page is it on? That's lecture 1. Where are we, Nathan? Here we are. Right. So we're at Moody. So my relative roughness. Alright, this is where I've grabbed it from. Galvanized. And the question says galvanized steel, I think. Galvanized steel pipe, we're taking it as the same roughness here. Okay, galvanized steel, galvanized iron, we can take it as the same. Alright, so that sits in here somewhere. Alright, so remember what we do is we follow, if I look at point 002, my trend line's not quite flat, but it actually curves up as we get closer. And same with point 001, sorry. So when we come anywhere between and extrapolate data, we have to follow that trend line. So our lines must curve up as we go. So using about halfway in here somewhere, as well as our Reynolds number, which is 2.83 by 10 to the 5, which is here somewhere. Alright, sitting about here again. Alright, come across. What we do is we end up with the same. We end up with our friction factor, 0.0225. This is from Moody. So Moody diagram. Alright, so what do I need to calculate? Well, firstly, let's calculate my losses due to friction. My loss due to friction. Sorry, I know this is probably a bit confusing. I normally write in cursive, and I'm trying to get used to writing in all capitals. So that's why I'm chopping and changing between handwriting here. So apologies for that. Cool. So my loss due to friction is F L on D times by V squared on 2G, which equals, so there should be an F as well. Oh, it looks so wrong. That's okay. So let's go through 0.0225. The length, what is my length of pipe? 60 meters. 0.1, 2.55 squared. Alright, and what do we end up with? 4.47 meters of head loss. Alright, funny fact, it's what we got before. Alright, they're the exact same numbers. Now let's go through and let's do the fittings. So, how do we set this out again? My fitting, K factor, my number of fittings, and then my sum of K. What fittings do I have? Well, I have one hinged disc foot valve with a strainer. I have 4 standard 90 elbows, 4 union screwed, 2 gate valves, 1 sudden enlargement to a pressurized tank. The other thing that I do have in here is I have 1 gate valve that is open and the other that's half closed or half open. Alright, so you can go through and have a look at those appendices again and find out the values. I'm just going to write them out. My elbows, my standard elbows, some unions, gate valves, and I have one that's open, I have one that's half open. And I have an enlargement. Alright, no, it's not the most neat set out, but it will do for now. These here won't, that's quite annoying. It's better, okay. So, foot valve, K factor, 2. How many do I have? I have 1, gives me a K factor of 2. My elbows, 0.9, how many of these did I have? I had 4. Unions was 4. My open gate valve, my half open gate valve, 1. How many of these did I have? I had 1, 1, and 1. So multiply these out, 3.6, 0.2, 0.2, 5, and 1. So my sum of K, adding all of these here together, is 12. So my head loss due to fittings, that's my fittings, is equal to K V squared on 2G. K is 12, V is still the same, all over 2G. Alright, what we get here is 3.98 meters. Alright, so what we're going to do is we're going to find our total head loss, or our system head loss. So our head loss in the system is equal to my head loss due to my fittings plus my head loss due to friction, 4.47, and all of this equals 8.45 meters. So there's my head loss, or my system head loss. Alright, adding in friction and fittings, again you could use that one formula and be done with it much quicker. Alright, so what have we got next? Determine the length of a 100mm pipe that is equivalent to a fully open globe valve. Alright, so we've done this before. All we need to do is we work out the loss, go through, calculate your LE. I will leave 11.5 and 11.6 for you guys to tackle. I'll go through 11.12. Alright, these ones here are not difficult. It is similar to what we did in 2.6. So 11.12, let's go through this. Let's clear it. Let's take a screenshot of this and let's bring it in. Alright, is this still recording? Cool. Oh, 30 minutes. Sorry guys, it's a long one. Alright, so what have we got here? A plastic pipe of diameter 50mm and a length of 30mm carries water with a velocity. A reducing section is fitted to the pipe and then it shifts. Alright, the first pipe, determine head loss, and then the total head loss. Okay, got dynamic viscosity, and it looks like they have given us solutions here, which is quite nice of them. Alright, so let's go through and do that. So what's happening here? Well, I have, by the looks of it, pipe going here, 50 mil diameter. Diameter. I have a velocity running here, 2.5 meters per second. And then I have a reducing pipe is fitted. So somewhere here it shrinks and comes this way. Alright, it's a bit extreme, but that's how it looks. Something like that, and that drops down to 40 mil. So here I have 40 millimeters. Okay, how do I go about this? Well, V, A1, A2, so we know from our continuity equation. Alright, I hope you all remember this one. V2 is equal to A1 on A2 by V1 equals pi by 0.505 squared over 4, all divided by second pipe. V1 is 2.5 meters per second. What we end up with here is we end up with a V2 of 3.9 meters per second. So that's the velocity in here, which is V2. Okay, now what? Well, I have one Reynolds number here, one Reynolds number here. So I have a friction coefficient through here and a friction coefficient through here. So I have two of them. Alright. This is why it's split up. Let's go through part A first. So for A, the head loss in the 50 mil pipe. Well, I need to calculate first. I need to work through my Reynolds number, which is rho velocity diameter divided by viscosity. Got the viscosity here. We have water. Alright, water. So it's 1,000. 2.5 times the diameter, 0.05. All divided by mu, which is this here. And our Reynolds number is equal to 1.39 by 10 to the power of 5. Now, tricky bit. What is this pipe? So the pipe, it's a plastic pipe. Plastic pipes are smooth pipes. Alright, go back through your notes, that's what you'll see, is the plastic pipes are smooth. So what we're looking at is where the smooth pipe line is, which is the lowest friction coefficient. So we have calculated our Reynolds number, which is 1.39 by 10 to the 5. So over here somewhere, we know it's a smooth pipe. So I can come up in here to where my smooth pipes are. Here I can come across. And what I work this out to be, reading off this, is just under, it's down here. So it's just under 0.17. So I work out my friction with normal handwriting. Friction to be equal to roughly 0.168. That is from Moody diagram. Alright, you need to reference this because we do have formulas as well, and I need to know which one you've used. Because if you use a formula and you get it incorrect, you tell me it's from the Moody diagram and you're very far out, the marks here are obviously going to be different. So my go-to is always Moody. I personally don't use the formulas, and that's what I would do if I was you as well. So now that I've got Reynolds, I've worked out it's on a smooth pipe, worked out my friction factor, what I can do So I can work out my head loss with friction. And what do I have? Well, I have my friction, my length divided by diameter, v squared on 2g. The length of this pipe is 30 meters. The diameter is 50. Velocity was 2.5. This equals to 3.21 meters. This is the head loss in the 50 mil section of pipe. Alright. So that is the loss due to friction. Now, we're not going to look at any fittings until we do part C. So we'll look at part C in a minute. So this is done. This is the head loss due to friction. Now the head loss due to friction in the 40 mil pipe. So part B. My head loss in that pipe due to friction. Alright, it's the same thing. It's equal to F L on D V squared on 2G. To calculate F, I need to go back through and I need to work out my Reynolds number. So let's do that. My Reynolds number on this side, using the same formula, rho by V by D all over. It's the same fluid, it's incompressible. And this Reynolds number is 1.73 by 10 to the power of 5. Chuck this in using obviously it's still a smooth pipe, it's still plastic, and what you'll end up with is a friction factor of 0.16, sorry, 0.016, and that's from Moody. Alright, now we come back to our formula, 0.016. The length is 20 meters, given in our question. Diameter is 40 mil. Velocity in this case is 3.9 squared, 1.81. And the friction loss in here is 6.2 meters. Alright, so we've answered A, we've answered B, now let's answer C. Total head loss allowing for a sudden entrance, exit, and contraction. So I guess what we have to look at here is where is what? What's happening where? Well, sudden entrance, exit, and contraction. Cool. So, fittings. Have the K value, and I have my number, then I have my sum of K. So let's do this one here with the 50 mil pipe. Change color. 50 mil pipe, we'll put through here. After we do that, we'll do the 40 mil pipe. So what is the 50 mil pipe? What's happening? So if I assume it's attached to a tank through here somewhere, I have a sudden entrance. And then I also have a sudden contraction at this point here. This is where we have to be careful because the K is directly related to the velocity. The velocity on this face here is still the 2.5 meters per second. After this point, it speeds up. If I chuck this in at 3.9 meters, I'm going to get extra head loss, which is not correct. Alright, so it's still this water that's flowing through, doesn't speed up till after the contraction. So, for the 50mm pipe, I have a pipe entry, and I also have my sudden contraction. K values for these, my pipe entry, go back through your appendix or your notes, and this one here is 2, 3. How many have I got? I've got 1 and I've got 1. Sum of K, 0.5, 2, 3. So my total sum of K is equal to, just adding these up. Now for the 40mm pipe, what do I have? So looking at my 40mm pipe, all that I have here is my exit. Oh, sorry, up here. This, we're not told anything what happens over, so we just assume it runs out. That's our pipe exit, which is this bit here. So I have my pipe exit. Again, go through, what you'll find is it's a K value of 1. I have 1 of them, so my sum of K is equal to 1. 1.0. Alright, so now what we can do is I can work out my losses due to fittings and then add them together. Alright, so that's how we work out our total head loss. Loss due to friction in pipe 1 plus the loss due to friction in pipe 2 plus the loss due to any fittings through here. Alright, so let's go through and do that. So for my head loss due to fittings, still looking at my 50mm diameter pipe. The losses in this is K V squared on 2G. Sum of K 0.73. 2.5 is what's flowing in that first pipe. It's not G anymore, we have numbers. And this here is 0.233 meters. Now my head loss due to fittings in my 40mm diameter pipe. Sum of K V squared 2G. 1. I got 1. That was our K that we worked out over here. Alright, V, this is V2, this is V1. 3.9 squared all over 9.81. Alright, and what you find this here is 0.775 meters. So that's what I have. My loss due to fittings in the first bit of pipe, my loss due to fittings in the second bit of pipe. I have my loss due to friction in the first bit and the second bit. Now what I can do is add them up. So my total head loss equals 3.21, which is my loss due to friction in pipe 1. 6.2 is my loss due to friction in pipe 2. My loss due to my fittings in pipe 1. And my loss due to fittings in pipe 2. So there's my total head loss here. Alright, so I hope that makes sense. as to how we set things up, how we find things out. Please do be aware that it is relative to the speed, alright? It's relative to the velocity head. That's why I need to be careful as to where we're taking the fittings from. So I'll leave you guys to do 11.5 and 11.6, and we will go through that in class next week. Thank you. Any questions, please just send me through an email.